Hey everyone, welcome back to our final lecture. So over the past 8 weeks, we've explored most of the main topics covered in middle school competitions. So all that's left for those topics is just for you guys to just like do more practice questions, do some past tests and all that. There are some great resources on AOPS or Brilliant, and I think even Khan Academy has some. So you can check those out. So today we'll be discussing one last topic in algebra, which is complex numbers. So these are typically covered in Algebra 2 in our school curriculum. So they fall just at like the edge of like late middle school competition to like as you go through high school competition, they'll become more frequent and more common. So the handout is on our website as usual, so feel free to pull that up to help you follow along. And so to get started, we can look at the classifications of numbers for a bit. So an introduction to complex numbers. So most of you guys, when you started math, like early on, like in elementary school, you just started with like positive counting numbers. So these were like the natural numbers like 1, 2, 3, 4, and so on. Then you got introduced to like the idea of zero, the whole numbers, and then to the integers. So you include negative numbers like -1 and -2. And they seem really natural now, but I'm sure like when you first heard them, conceptually they're very different from positive numbers. So after the integers, we introduced the concept of fractions and rational numbers. So this would be in the form of like a over b. And then from then on, you went on to irrational numbers. So you had like radicals like square root of 2 or the cube root of 75. And you also had more transcendental numbers like pi and e, etc. So adding on to these, we created the real set of numbers, which is what most of you guys work with pretty comfortably at this level of math. So the next step to take forward would be imaginary and complex numbers. So these numbers come from the question of, well, what happens when you take the square root of a negative number? Let's say the square root of -1. Well, none of the real numbers would satisfy it. So what we do is we create a new like genre of numbers. And this leads to the entirety of the imaginary and complex numbers. So an imaginary is just some number that is a multiple of I. So you could think of I as like the base unit of imaginary numbers. It would be the equivalent of 1 to real numbers. So the unit imaginary number, like I said earlier, I is equal to the square root of -1. So for example, 4i would just be 4 times I. So if you squared it, it would be -16. So 4i equals the square root of -16. Complex numbers, however, are a combination of these two. They have a real part, like, and they also have an imaginary part. So they're in the form of a plus bi. So unlike real numbers, we can't order complex numbers like on a number line as we traditionally thought of numbers. Instead, what we do is we put them on this plane. We have one axis that represents the real component of the complex number. So anything on this number line would just be what we're used to, like 1, 2, 5/4, the square root of 2, and even pi lie on this line. Meanwhile, we have another axis that runs vertically, which represents the imaginary numbers. So this is where numbers like I, 4i, and so on would be. And like the Cartesian plane, when you have a point in the plane, it corresponds to where it lies on both of the axes. So at a point 3, 4, this number would represent 3 plus 4i in the complex plane.
All right, so now moving on to some operations and stuff that we can do with complex numbers. So operations for complex numbers work in basically the same way as they do with normal numbers, except you basically group together imaginary components and real components separately. So we'll work through the combination of the two numbers, 3 plus 2i and -2 minus 4i. So first, if we want to see the sum of these two numbers, it's, as we said before, you just have to group together the real components and the imaginary components. So we'd get 3 plus 2i minus 2 minus 4i. The real components come together to form 1, and the imaginary components come together to form negative 2i. So the sum of these two numbers is just 1 minus 2i. Similarly, if we want to take the difference, it would work in the exact same way. And once again, if we group together the real components and the imaginary components, we get 5 plus 6i. Multiplication, on the other hand, may seem a bit more complicated, but fundamentally it works the exact same way as we do in normal algebra. So if we have 3 plus 2i times negative 2 minus 4i, it's basically a matter of distributing each of these terms across to the other ones and just expanding. So we would get this set equals negative 6 from these first two terms, minus 12i from the 3 and negative 4i, minus 4i from the 2 and negative 2, and then minus 8i squared. So now right away you can group together these two to get negative 6 minus 16i minus 8i squared. But now we have this I squared term that isn't particularly nice. But in order to get rid of it, we can just remember what I is by definition. Since I is equal to the square root of negative 1, that means that I squared is equal to negative 1. This basically just becomes negative 6 minus 16i minus negative 8, which equals 2 minus 16i. And then finally, we have division, which is slightly more complicated. So if we want to take 3 plus 2i divided by negative 2 minus 4i, we can't right away see what to do with it. But if some of you had experience dealing with irrational numbers in the denominator and rationalizing the number, you can notice that we can try using a different square factorization to get rid of the denominator's imaginary component. Specifically to do this, we have to introduce a concept called the conjugate of an imaginary number. So if we have some number a plus bi, its conjugate would be of the form a minus bi. And this looks a lot like the difference of squares factorization, and that's really useful since if you multiply these two things together, this turns into a squared minus bi squared, which equals a squared plus b squared, which is a real number. So we can use that to clear the denominator for this fraction over here by multiplying the top and the bottom by the conjugate of negative 2 minus 4i, which would be negative 2 plus 4i. So for the top, once again, we just have to expand it. And this would result in, if we went through the same steps as we did before, this would result in negative 14 plus 8i in the top. And on the bottom, as we showed over here, it's equal to a squared plus b squared. So a squared would be 2 squared, which is 4, and b squared would be 4 squared, which is 16. So this simplifies to negative 7/10 plus 4/10 I. And a useful thing to check these whenever you're dealing with complex numbers, Google in fact can calculate these in their own calculator. So if you just type it in the search bar, you can always check your answers for these complex numbers calculations, which is pretty nice. And finally, another concept with complex numbers is the magnitude of the number, which is basically if we graphed it on the complex plane, it would be the distance from the origin to the point. And using the Pythagorean theorem, that just has the value. We express the magnitude with absolute value signs. So we have a complex number w. The magnitude of w, if w equals a plus bi, is equal to the square root of a squared plus b squared. And one interesting thing, we can express the conjugate by drawing a line over the variable. So if we do w times the conjugate of w, this would equal a squared plus b squared, which is equal to the magnitude of w squared. And this is a property that comes up somewhat frequently in competitions. Another way to define complex numbers instead of x, y coordinates is the polar grid, where instead of using an x and y coordinate, we specify an angle and a distance. So polar grid looks something like this. If we have this point over here, we specify by the length of this line and the angle here. So we can use a bit of trigonometry to see what this would mean. The vertical length is equal to r sine theta, while the horizontal length is equal to r cosine theta, which means the overall value of this point, if we convert it back to rectangular, would be r times cosine theta plus I sine theta. And a common way that this is abbreviated in competition math is cis. So we write this as r cis theta for cosine I sine. And to convert back, r is just the magnitude of the distance. So r is just equal to square root of a squared plus b squared. While on the other hand, theta is a bit more complicated. Theta is what we call the argument of the function. And to convert back, you'd have to use tangent inverse of a over b. Unfortunately, this only works in special cases where the angles are really nice, like a 30-degree, 45-degree, or something like that. And we can do a lot of nice operations with multiplication and division in polar form. The main function is that, oh yeah, you're right, it's b over a, sorry. So the main function with the cis format is that we can multiply and divide extremely easily. And this comes due to the property cis of a times cis of b is equal to cis of a plus b. The derivation of this comes from some trigonometric identities, which is shown in the handout, but we'll skip over that for now in the lecture. But as a summary, it basically just expands this back into its original form of cosine plus I sine, and looks for the angle sum identities. And from this, we get some other identities, such as 1 over the cis of alpha of some angle A is equal to cis of that negative angle A. So that would mean that if this was that also happens to be the conjugate. So if this is an angle, some complex number W, the conjugate of that number would be negative theta, which would be theta below the axis. And this would be the conjugate of the value of W. And additionally, one other important theorem is called the Mohr's theorem, which is an extension. It basically means that if we have some complex number z, which is equal to r cis theta, then z to the n is equal to r to the n times cis of n theta. And this is basically a direct application of this original theorem, or this original equivalent, since we'd just be multiplying z by itself again and again. The final format, which we'll be going over, is a lot more theoretical, and it's the exponential form. So one of the most famous results of this form is Euler's identity, which is e raised to the pi I plus 1 equals 0. So this expression itself is rather complicated. Like, how do you even raise something to an imaginary power or even an irrational power? So for now, don't worry too much about why it works. It's a really interesting proof, but it relies mostly on calculus and Taylor expansions, which is significantly beyond the scope of middle school competition math. Instead, we can use this expansion and we can use this form in middle school competition math and beyond to prove some easy rules. So the more general form of this is that e raised to theta times I is equal to cis theta. And right now, this does take a bit to prove, but as I said before, this is a calculus proof, so we can't exactly do that right now. But if we take this as a given, we can easily prove the identities from before. For example, if we want to multiply two complex numbers, e to the alpha I times e to the beta I, we can simply use exponent rules and add them together. And this becomes e to the alpha plus beta times I, which is the same as before. Finally, we'll move on to another topic called the roots of unity.
All right, so the roots of unity are one of the most important topics, especially in competition math when it comes to imaginary numbers. So what are roots of unity? So these are like, well, it's in the name. They are the roots of unity, where unity is just one. Meaning that for some integer value like n, if you have a root of unity raised to the nth power, it will equal 1. So in this case, we would call them the nth roots of unity. So there are always exactly n nth roots of unity, meaning if you look at the number of square roots of 1, you have -1 and 1. These are what we call second roots of unity, and there are two of them, -1 and 1. And if we take the cube root, well, traditionally we would think, oh, there's only one cube root, and that is 1. But there are actually two more complex roots to the solution. And these are what we call the third roots of unity, and so on for all n. So the easiest way to find them is to actually use the exponential form we just learned, which is also why we introduce it despite not being able to show you the proof without higher level maths. So to find roots of unity, we want an imaginary number or a complex number in the form of e to the theta I, all raised to n. And using our knowledge of powers, we know that this simplifies into e to the n times theta times I. And we want this to be equal to 1. So this will only be equal to 1 if n times theta is a multiple of 2 pi, since e to the 2 pi is equal to 1. And since the cis of any multiple of 2 pi is 1, as the imaginary sine component will be 0, while cosine will be positive, and therefore we want theta to be in the form of 2 pi times k over n, where k is some integer between 0 and n. So you can see that if theta is equal to this, when we multiply by n, this is always a multiple of 2 pi, but it does not repeat itself over and over again. So once we get k is greater than n, you would have something that is greater than 2 pi, which would overlap with one of the earlier solutions. So this results in an easy proof of our identity earlier, where we show that there are exactly n roots of unity for the nth root. So for k is equal to 0 and all the way until k is equal to n minus 1. So on the complex plane, what these roots of unity would look like would be that they would form a regular polygon with n sides, so that, so for example, if you had the 3/3 degree roots of unity, they would form an equilateral triangle with the roots being 1, -1/2 plus √3 over 2i, and -1/2 minus √3 over 2i. And something that is also very important about the roots of unity is that their magnitude is always 1. And this makes sense because when you take the magnitude to the nth power, it still has to be equal to 1. Therefore, the magnitude will always be 1. So now we'll move on to some of our practice problems.
All right, so our first expression is just basically another practice problem on algebra, on the basic arithmetic of imaginary numbers. So if we have that 2z plus I equals iz plus 3, we want to solve for what z is. So you can basically rearrange this by moving the I over to one side. So we get that 2 minus I times z equals 3 minus I. So basically to solve this, we can just divide both sides by 2 minus I as we would with normal algebra. And we get that z equals 3 minus I divided by 2 minus I. Now, in order to clear the denominator, we use our the conjugate as we discussed earlier. So the conjugate of 2 minus I would just be 2 plus I. So if we multiply the top and bottom by 2 plus I, we get the denominator becomes 2 squared plus 1 squared, which is 5, while the top becomes 6 plus 3i minus 2i minus I squared. And this simplifies to 7 plus I divided by 5. So that means that our answer, z, is equal to 7/5 plus 1/5 I. So this is basically a pretty simple problem. It just shows that you always want to group the imaginary parts separately and the complex parts separately. And you basically just deal with imaginary numbers in the same way as normal, the real numbers that you've done before. So on to our next question, which will highlight some of the properties of the conjugate. So we have complex numbers a and b that satisfy a times the conjugate of b is equal to -1 plus 5i, and we want to find the value of the conjugate of a times b. So one of the main properties of conjugates is that if we took the conjugate of a and b, we took the overall conjugate, this is just equal to the conjugate of a and the conjugate of b times the conjugate of the conjugate of b. But as all the conjugate does is flip the sign of the imaginary component, this thing is just equal to b. So that means the conjugate of a times the conjugate of b is just equal to the conjugate of a times b. So while this is a mouthful, hopefully it makes sense visually. So that means that this value is equal to the conjugate of -1 plus 5i, which is just equal to -1 minus 5i. So basically the main thing to highlight is that if you're taking a conjugate of two complex numbers that are multiplied together, you can basically split it up to each one of them and still multiply them together.
Okay, so for our next problem, suppose that a and b are positive integers, and they're integers such that a minus bi quantity squared is equal to 8 minus 6i, and asked us to evaluate what a minus bi is. So, well, first what we can do is just expand this. This is just a general strategy for any algebra problem. If we expand this, what we get is we have a squared, then minus 2abi, and then, well, bi squared would be negative b squared, so we have minus b squared. And this is equal to 8 minus 6i. Well, now we see that the real part of both of these numbers have to be equal, so we get that a squared minus b squared equals 9. And we also get that the imaginary parts have to be equal, so we get negative 2ab equals negative 6. So here we have a system of equations, and this is something that comes up fairly often when we're dealing with the rectangular form of imaginary numbers. And when we're multiplying them, we come up with system of equations which we can use to solve for the values. So, well, using our second equation, this means that a times b is equal to 3 if we divide both sides by negative 2. And since we know that both a and b are positive integers, that means a and b are either 1 and 3 or 3 and 1. And a quick check, we would see that 3 and 1 is the only solution, since we would have 3 squared minus 1 squared equals 8, which is true, and 3 times 1 is equal to 3. So that gives us our answer that a is equal to 3 and b is equal to 1, so our number is 3 minus I. Well, yes, we could have, like Anand said, we could have taken the square roots on both sides, but that's a bit hard because taking the square root of 8 minus 6i isn't the cleanest thing. You could change it into some sort of cis form and then use the half angle theorem, but that is a lot messier than just solving a system equation, since this is pretty straightforward.
Oh, wait, also, yeah, you're right. We missed the solution. We could have also had the, or no, we didn't miss the solution because it said over here that they're positive integers.
Yeah,
That's where the other
problem specifies positive integers.
Yep. All right, now onto our next problem. So this thing is actually making use of some of our series knowledge from the first lecture. So we want to find for what value of n is I plus 2i squared plus 3i cubed all the way up to ni to the n equal to 48 plus 49i. So once again, we want to look at the imaginary and real parts separately. So first, let's look at the imaginary parts. We'll have this I. This 3i cubed will simplify to minus 3i. The next term would be plus 5i, and so on. So this alternates basically, the sum itself alternates to 1, negative 2, 3, negative 4, and so on. Which means that 49 should be the 49th imaginary number, which will be 97. That means that then we can do the same thing with real again. So first thing starts out with 2i squared, which should be a negative 2. Then I'll go to 4i fourth, which is just plus 4, minus 6, and so on. And once again, we'll get that the 97th term is what will result in 48 as our sum, which means that n is just the 97th, or n is simply just 97. Right?
So here we have that we want to find C if that A and B and C are all positive integers, which satisfy C is equal to A plus BI quantity cubed minus 107I. And it gives us that the definition of I. So, well, let's unpack this a bit. So we know that C is a positive integer, which means that we have this complex number cubed minus 107I has to equal a positive or a real number, a positive real number, an integer. So, well, if we expand this out, we get that C plus 107I, if we move the 107 to the other side, is equal to, well, A plus BI quantity cubed becomes A cubed minus plus 3a squared bi minus 3ab squared minus b cubed I. So if we group together the real and the imaginary terms, this becomes a minus 3ab squared plus 3a squared b minus b cubed times I. So we know that two complex numbers are equal if and only if their real parts and the imagined parts are equal. So we get another system of equations where we have a cubed minus 3ab squared equals c, and 3a squared b minus b cubed equals 107. So we can factor out our second equation, and we would get that 107 is equal to 3a squared minus b times b. So at first, this may seem pretty hard. We have a system of equations, but only one of them is an actual equation where the other one we're solving for c. So there would technically be no solution to this. But like one of our earlier problems, it also tells us that a and b are both positive integers. So we can use a bit of what we learned with divisions and factors from our number theory lecture. So 107 is a prime number. You can check that on your own. So this means that b has to be a factor of 107, obviously. So we have two cases, either since b is a positive integer, so b is equal to 1, or b is equal to 107. So if b is equal to 107, we get that 3a squared minus 107 squared equals 1. So we get 3a squared equals 107 squared plus 1. But if you notice, 107, if you look at it in mod 3, it becomes -1 mod 3 or 2 mod 3. So if you square it, it becomes 1 mod 3. So that means 107 squared plus 1 mod 3 is 2, which means that it can't be equal to 3a squared since we know a is an integer. So 3a squared is a multiple of 3. So this has no solutions. So that means b has to equal 1. And this would give us that 3a squared equals 108. And so, well, that means a squared is equal to 108 over 3, which is 36, which has the solution is equal to 6. And note again how we only have one solution. -6 is not valid since we know a is a positive integer. So plugging this back in, we know that a is equal to 6 and b is equal to 1. Thus, we have that c is equal to 6 cubed minus 3 times 6, which is 198. If we plug this into the real part of the imaginary number, so a cubed minus 3ab squared. So this gives us our answer, which is 198.
All right, now on to our next problem. This problem is one that deals with mainly the roots of unity, though it doesn't look like that right off the bat. So we can start out by looking at this expression, z squared plus z plus 1. It looks somewhat familiar, especially if you remember the factoring lecture, since this is actually a component of the difference of cubes factorization. So for this, if we multiply both sides by z minus 1, we would get that this equals z cubed minus 1 equals 0. But we have to remember that we can't let z equal 1. This means that is basically one of the third roots of unity, such that z cubed equals 1, but z does not equal 1. So knowing that z cubed is equal to 1, we can simplify this overall thing very easily, significantly. First of all, z to the 97 would equal z to the 96 times z, which is equal to z cubed raised to 32 times z, which is just equal to z. So we can similarly apply that to each of the other terms, and that would simplify to z plus z squared plus 1 plus z squared. And so now we can simplify this expression using our original identity that z squared plus z plus 1 equals 0. So we can group this up as 2 times z plus z squared plus 1 minus 1 which would equal 2 times 0 minus 1, which just equals -1. So basically an important thing to note from this problem, whenever you see a factorization that looks like z squared plus z plus 1, you should always consider that it's referring to the third roots of unity, since that's part of the factorization of a difference of cubes. There are also factorizations for higher powers, as we've seen in our earlier lectures, but those don't show up as commonly in competition math problems.
Also, something to be careful of is if it's in the form of z squared plus z plus 1, z equals 1 is explicitly not a solution, even though it is one of the third roots of unity. All right, so moving on to our next question, we have let z be a complex number such that z plus 1 over z equals 1. Find z cubed. So, well, at first you might think that, oh, 1 over z is just the conjugate of z, and then, well, you would try to evaluate what z is from that. But there's actually a much easier way, since we can just clear the denominator first by multiplying both sides by z, and we get z squared plus 1 equals z. So this is actually pretty familiar to what we saw in our last question. Well, not quite yet, but if we move the z over to our left-hand side, we get z squared minus z plus 1 equals 0. And this is similar to what we had in the last question, except instead of a minus z, we had a plus z. So in our question before, we had a difference of cubes where we multiply by z minus 1. Here we actually have the factor of a sum of cubes. So we multiply by z plus 1 here. This becomes z cubed plus 1 equals 0. And that just gives us that z is equal to negative, or z cubed is equal to -1 if we solve for z cubed. Which just gives us our answer. So z cubed is -1.
All right, now on to our next problem, which is a bit more abstract. So let S be the set of complex numbers of the form a plus bi, where a and b are integers. And we see that z in that set is a unit if there exists another element of that set such that zw equals 1. And we want to find the number of units in S. So to do this, we can first look at magnitudes. If a and b are both integers, the smallest possible value would be 0 plus 0i, which obviously doesn't work, since that doesn't have a magnitude of 1. So the next smallest magnitude is 1. That means that all the magnitudes are at least 1, so if the product of two of them is 1, both the elements must have the exact same magnitude of 1. Since if either, let's say, the magnitude of zw is also equal to the magnitude of z times the magnitude of w. So basically, in order for this to equal 1, since both z and w are as small as possible, both these have to be 1 as well. That just means that this is just roots of unities with integer coefficients. So once again, the only possible values that work are 1, -1, I, and -I. Since each of these has a magnitude of 1, and they can each be paired with themselves in order to square 1. Now, on to one more question that explores roots of unity. So we have 24 different complex numbers z, such that z to the 24th power is equal to 1. And we want to find out for how many of these is z to the 6th equal to a real number. So at first, this may seem easy. Out of the 24 roots of 1, only 6 of them can satisfy z to the 6th equals 1. Since this is equal just a polynomial, right? So that's right, so the answer is 6, right? But in fact, we actually forgot a case. So we want z to the 6th to be real. And since they're roots of unity, that means that z to the 6th equals plus or minus 1. Since equaling 1 is not the only solution. So in fact, all we need is that z to the 12th equals 1, which gives us 12 solutions. So this problem basically could easily trick up people if they're approaching it too quickly, since you just go straight to z to the 6th equals 1, which is wrong since you forgot that real numbers don't force 1. So yeah, in this case specifically, we have to account for -1 as a solution as well, which gives 12 total solutions.
All right, so for our next question, we are given that z is a complex number such that z plus 1 over z equals 2 cos 3 degrees. And it asks us to find the least integer that is greater than z to the 2000th power plus 1 over z to the 2000th. So here we're getting into a bit of the more difficult competition questions that require a bit more application of complex numbers. So, well, we've sort of seen the expression z plus 1 over z equals some value before, but this time it's not as nice. Before it was equal to 1, now it's equal to 2 cos of 3 degrees. I don't think any of us know what cosine of 3 degrees is. So we can actually use the method we mentioned earlier but didn't implement, which was we treat 1 over z as just the conjugate of z. So we have z plus the conjugate of z equals 2 cos 3 degrees. And so let's say that z is equal to cis theta for some theta. Or actually it should be in the form of r cis theta since we don't know its magnitude. Well, that means that the conjugate of z would just be r cis negative theta. And the sine of negative theta is equal to negative sine of theta. So when you add them together, they cancel out. So all this so if you add z and the conjugate of z together, all that's left is 2 times r cos theta. And it is always real because the conjugate has the opposite imaginary part as its original number. So that means that we have that z plus z bar is equal to 2r cosine theta, which is equal to 2 cosine 3 degrees. So we already know from this that r is equal to 1 and cosine theta is equal to cosine of 3 degrees. So theta is equal to 3 degrees. So we've already figured out from this expression what z is. We know that z is equal to cis 3 degrees. So if we take z to the 2000th power, using what we learned from our brief coverage of how taking powers work with cis, we know that this is just r to the 2000th power times cis 3 times 2000. Since r is equal to 1, this is just cis of 6000 degrees. Well, 6,000 is obviously a really big number, so we take this mod 360, so it's somewhere in the range of 0 to 360 degrees, or one full circle. And if you take this mod 360, it actually just becomes cis of 240 degrees. So now that we know what z to the 2000 is, we can use the same logic we used earlier, where we have z to the 2000 plus the conjugate of z to the 2000, so z to the 2000 bar. And this should just be equal to 2 times the real part of z to the 2000, which is just cosine of 240 degrees. So this is just 2 times cosine of 240 degrees. Well, cosine of 240 degrees is negative 1/2. So that means that this ultimately simplifies to 2 times negative 1/2 equals negative 1. So we're done. But actually, careful, because the question also asks us to find the least integer that is greater than, so strictly greater than negative 1, which is obviously not going to be negative 1. So we want to find the next largest integer, which would be 0. And this is actually pretty funny because this was an older Amy question, and negative 1 definitely cannot be an Amy answer. And 0 is the smallest possible answer you can get for an Amy question. All right, so next we have that here we have a problem. The number of ordered pairs of real numbers, a and b, such that a plus bi all to the 2002th power equals a minus bi. So this problem introduces a few of the more common patterns with competition problems. So we have that, this imaginary number to this large power is equal to its conjugate. So thinking of numbers in rectangular form, especially with powers, is generally not a good idea because you get these weird system of equations that are not very nice. It's much easier to think of them either in cis theta form or e to the I theta form. So here, let's look at it as cis theta. So let's rewrite a plus bi as r times cis theta. And this just makes it much easier. So if we look at a plus bi to 2002 equals a minus bi, we can rewrite this equation in our cis form, which would give us r times cis theta to 2002, which we know equals r to 2002 times cis of 2002 theta. And you can already see how much easier a cis theta makes taking powers. And this is equal to r cis of negative theta. So, well, we can see that the magnitudes are r to the 2002 and r respectively. So that means we get that r to the 2002 equals r, which only has one real solution, which is 1, and magnitude is always real. So we know that r is equal to 1. So that means we just have that a plus bi is cis theta, so we get that cis of 2002 theta is equal to cis of negative theta. Well, when does this happen? Well, if you think of it, if you multiply both sides by cis theta, if you multiply it all by cis theta, well, what you would get is that on one side you have cis times 2002 theta times cis theta. Oops. Times cis of theta is equal to, well, cis of theta and cis of negative theta are conjugate. So this is actually just equal to 1. And when we're multiplying in cis theta form, we just add the angles and multiply the magnitude. Since both magnitudes are 1, we just add the angles, which gives us cis of 2003 theta equals 1. And you can just see this is actually just in the form of roots of unity. These are the 2003rd roots of unity. So where theta is in the form of 2 pi k over 2003, where k is less than 2003. So this actually gives us 2003 solutions. So that would be our answer. But we have to be careful again because, well, earlier when we solved for the magnitude, we actually forgot one case. Obviously, r to the 2002 equals r has r equals 1 as a solution, but r can also be 0. We can have just the complex number 0 plus 0i as a solution. So when r is equal to 0, we actually have one more solution. So our answer is 2004, not 2003. So this problem kind of just highlights something to be careful about when you're finding magnitudes, when you have equations in the form of r to some power equal r. And overall, this type of problem is very common in competition math, where you have some complex number or some roots of unity to some very large power equals to some other root of unity or some other, like its conjugate, and you have to solve for it, and you just get, and this is why roots of unity is such a big part of competition math, is because it is very recurring, especially when you have like the large powers, and competition is very much like these kinds of problems. So moving on to our next problem. So here we have a sequence of complex numbers z0, z1, z2, dot, dot, dot. And this is defined by z of n plus 1 equals I times z of n over the conjugate of z of n. So suppose that the magnitude of z of 0 equals 1. How many possible values are there for z of 0 if z of 2005 is equal to 1? Not its magnitude, just its value. So, well, okay, we can kind of get the semblance of roots of unity from this. We see that the magnitude is equal to 1 and so on. But let's try to break down the rule that they gave us some more. So we have z of n plus 1 equals I times zn over the conjugate of z of n. Well, 1 over the conjugate of z of n, that's just equal to z of n. So if we rewrite this, we have z of n plus 1 equals I times z of n times 1 over the conjugate of z of n, and that is just equal to z of n. So this is just z of n squared. So that immediately makes this much less intimidating compared to this fraction that we had earlier with its conjugate and all that. So you can see how this algebraic manipulation is helping us advance with this problem. So as we continue, well, we know that z of n has a magnitude of 1, or z of 0 has a magnitude of 1, I has a magnitude of 1. So we can see that if z of n has a magnitude of 1, then z of n plus 1 has a magnitude of 1. So that means all of these terms, z of 1, z of 2, z of 3, so on, all have a magnitude of 1. So this is something that we kind of hypothesized earlier, since we saw that z of 2005 was equal to 1, but we sort of just confirmed it just now with our algebraic manipulation. Now, so we have our new rule that z of n plus 1 equals I times z of n. So let's break down how this transforms it. So one of the nicer ways to think of complex numbers, especially in like the cis form, and when you're taking powers, is just geometrically, where you're rotating the root of unity around the unit circle. So if you had z of 0, when you square it, you just double the angle between it. So if we had z of n is equal to cis theta, z of n squared, like we figured out earlier, is cis of 2 theta, and this is just doubling the angle. And when we multiply by I, well, I is just equal to cis of pi over 2. So when we multiply these two, what we actually get is that z of n plus 1 is equal to cis of 2 theta plus pi over 2. Now, so this helps us a bit, but we're still not quite sure how to progress. So another common tactic, not just in algebraic or complex number problems, just in general, is just if you have like a sequence or a series or some sort of pattern, you can just plug in smaller values. That always helps. So we know that z of 0 is equal to 1. So let's define z of 0 as cis theta, ignoring what we just did earlier, since that was for a recursive rule. So that means z of 1 would be equal to cis of 2 theta plus pi over 2. Z of 2 would be equal to cis of, well, 2 times what we had earlier, so 4 theta plus pi over 2 equals cis of 4 theta plus 3 pi over 2. Now, if we do this again, if we take z of 3, we have, we have z of 2 equals cis of twice of 4 theta plus 3 pi over 2. So that's 8 theta plus 3 pi. And then we add pi over 2 again. So this becomes cis of 8 theta plus 7 pi over 2. And we start to see a pattern. We see that z of n seems to be in the form of cis of 2 to the n theta plus 2 to the n minus 1 pi over 2. And although we can't really confirm it, it kind of makes sense based on how this rule works. Just based on like the recursiveness of this rule, we get that this general form is very likely to be the general form. And this is just something you do in competition math, where you find patterns, you make rules, you generalize it, and if they make sense, you just go with it. So we have our formula for the nth term of our series. So now it asks us, well, it tells us that z of 2005 is equal to 1. So we know that cis of 2 to the 2005 theta plus 2005 minus 1 over 2 pi is equal to 1, which means that 2 to the 2005 theta plus 2 to the 2005 minus 1 over 2 pi has to be equal to some 2 pi k. So, well, how many possible values can theta be? Well, let's take a closer look at this. So 2 to the 2005 minus 1 over 2 pi, well, that would obviously simplify to 2 to the 1004 pi minus 1/2 pi. Well, 2 to the 2004 pi is obviously a multiple of 2 pi k, so we can just ignore that actually. So what we get left is 2 to the 2005 theta equals minus pi over 2, or minus pi over 2 equals 2 pi k. So that means 2 to the 2005 theta equals 2 pi k plus pi over 2. Well, how many solutions are there to this? Well, if we have k is equal to 0, we have, well, if we solve for theta, we actually have theta equals 2 pi k over 2002 to the 2005 plus pi over 2 to the 2006. Well, our very rightmost term is always a constant, so that means the only thing that can change is our leftmost term. And you can see that these are actually just, well, they're the 2 to the 2005 roots of unity. So there are exactly 2 to the 2005 possible values k can be, such that each of these are still distinct. So k can be 1, 2, 3, so on, all the way to 2002 to the 2004, starting from 0. Two to the 1005 minus 1, sorry. Right? So that means that k has exactly 2 to the 2005 values, which means that there are 2 to the 2005 possible values for theta, which gives us 2 to the 2005 possible values for z sub 0. And this is from an AMC question, and if you actually looked at it, the answers were pretty funny because the answers were like 1, 2, 4, 2005, and then you had 2 to the 2005. And just like the vast difference between numbers made this problem probably not too difficult to guess, actually. So moving on to our last problem. So let n be the number of complex numbers z with the property that the magnitude of z equals 1, and we have that z to the 6 factorial minus z to the 5 factorial is a real number when divided by n. Find the number when n is divided by 1000. So here we obviously have roots of unity. We know that the magnitude of z is 1, and we have z to some power or some expression is a real number. So let's look at this. So we can actually factor the expression they gave us. So z to the 6 factorial minus z to the 5 factorial factors into z to the 5 factorial times z to the 6 minus 1. And 5 factorial is equal to 120. So we have z to the 120. Well, so we want this to be a real number. So let's look at z to the 6th first. We have z to the 6 minus 1 times z to the 1. Z to 120. So in order for this to be a real number, well, we can have either z to the 120 is a real number or z to the 6 minus 1 is a real number. So let's look at z to the 6 minus 1 first. Well, if you look at z to the 6 minus 1, well, it can be, well, in order for it to be a real number, well, -1 is obviously a real number, so z to the 6 has to be a real number. Oh wait, sorry. I think I have misspoken. Sorry. Okay. So this doesn't really. This is a bit confusing, right? We get z to the 6 equals 0, z to the 120 equals 0, but there are some other solutions that this doesn't account for. So what we can actually do is, instead of factoring it like this, we can create a new imaginary number. Let's say a. We let a equal to z to the 120. And we get that if you plug a into this, we get that a to the 6 minus 1 equals 0. Or is equal to a to the 6 minus a is equal to a real number. So that means that the imaginary parts of a to the 6 and a have to be equal in order for this number to be real. Well, the imaginary part of a to the 6 is just, well, sine theta of, if we had a equal to 6 theta, this would just be sine 6 theta equals sine theta. Well, you can either have that 6 theta equals theta, or so this leads us to two solutions. We have 6 theta equals theta. That's one family of solutions, which gives us 5 theta is equal to 0, or plus 2 pi k on both sides, obviously. So this gives us a family of solutions, in this case, the 5th roots of unity. But we also have the case where we have 6 theta equals 90 minus theta. And this is another family of solutions. So 90 degrees is the same as pi over 2 radians. So solving for this, we get that 7 pi is equal to pi over 2 mod 2 pi, or plus 2 pi k. And this gives us another family of solutions. So this would just be like pi over 14, 3 pi over 14, 5 pi over 14, and so on. Meanwhile, our other solution was just like 2 pi over 5, 4 pi over 5, and so on. So these solutions won't have any overlaps because if you look at the denominators, they're completely different. One is multiple of 5s, one is multiple of 7s. So one gives us 5 solutions, one gives us 7. So in total, we have 12 solutions from this. So that means there are 12 solutions for A. And since we know that A is equal to z to the 120, well, if we have z equals A, there are 120 solutions for z for any specific value of A. Since there are 12 unique values of A, we have 120 solutions for each of those A's, which gives us 120 times 12, which is 1,440. So when we take the remainder, when divided by 1,000, that becomes 440. All right, so I guess that's all we have for the entirety of the lecture series. So we probably won't be seeing you guys at least soon or in next week like we usually do. Homework will be posted again after the lecture after a few minutes. If you have any more questions regarding any of the questions we've done today, or actually any of the topics we've discussed over the past 8 weeks, feel free to ask us right now or shoot us an email in the future. And yeah, I guess that's all we have for today.
Yep, and thanks for coming to our lecture series. We really enjoyed teaching you guys, and hopefully you guys learned something.